One of the advantages of extravascular administration is that the drug can be formulated to control its release so that specific target blood concentrations can be achieved. Sometimes formulations release the drug very slowly, and this can result in flip-flop kinetics, which will be explained further in this video. Here we have plasma drug concentration time profiles for the same drug administered in 3 different formulations. Notice that although the absorption from the yellow formulation is slower than from the red formulation, we can see this because the Cmax is lower and the Tmax is later, the profiles are quite similar once the absorption phase has completed, and the decline is primarily representative of the elimination processes. Absorption from the purple formulation, however, is very slow, and this results in a very low Cmax that is sustained for quite some time. Notice also that the terminal portion of the purple drug concentration time profile is less steep compared to the other 2 formulations, which would suggest that the elimination rate constant is lower. But this is not possible since the elimination rate constant is dependent on the drug's clearance and volume of distribution, which are pharmacokinetic parameters that are independent of the formulation. So what is happening? Well, what we're seeing here is flip-flop kinetics, which happens when the rate of absorption is so slow that the absorption rate constant is smaller than the elimination rate constant. And as a result, the rate at which the drug is being absorbed becomes the limiting step, because the drug cannot be eliminated faster than it is being absorbed into the body, even though the body has the capacity to eliminate the drug much faster. It's important to recognize flip-flop kinetics because it affects how we interpret the parameters that we calculate from the plasma drug concentration time profile when we use the method of residuals. Usually, the slope of the terminal part of the plasma drug concentration time profile represents the elimination of the drug, and its slope on a semi-logarithmic scale gives us the elimination rate constant. Then we calculate the absorption rate constant through the method of residuals by feathering out the absorption process from the elimination in the initial portion of the time concentration curve. But when we have flip-flop kinetics, the terminal portion of the plasma drug concentration profile represents absorption because the drug cannot leave the body faster than it's being absorbed, and its slope on a semi-logarithmic scale is the absorption rate constant. As a result, that line that we calculate through the method of residuals during the initial portion of the time concentration curve represents the elimination processes, and its slope is the elimination rate constant. It's important that you understand flip-flop kinetics and also that you understand that it's not possible to recognize that we have flip-flop kinetics unless we already have pharmacokinetic data for the drug from other formulations. These formulations should either have been administered intravenously or should release the drug immediately so that the absorption rate is much faster than elimination. We are then able to recognize that we have flip-flop kinetics because the terminal slope is less steep than for the other formulations. And once we've recognized this, then we need to realize that the terminal slope is not the elimination rate constant, but rather the absorption rate constant, and we need to use the slope of the initial portion of the profile when we calculate the pharmacokinetic parameters like volume of distribution and clearance, or when we want to calculate what dose we need to use to achieve target steady-state concentrations.